Tonight we are going to try to answer a very simple question. How big is TON 618? And the answer is going to feel wrong. Not wrong because the science is broken. Wrong because the number is so large that it stops behaving like a number. It starts behaving like a wall. You have probably heard the name before. A monster black hole. A cosmic giant, a dot in a photograph from 1957 that later turned out to be one of the most extreme objects ever measured. But most of what gets said about TON 618 is either exaggerated, out of date, or missing the strangest part. Because in more recent years, astronomers have gone back and looked at TON 618 again, with different emission line methods and improved calibrations. And the story has shifted. TON 618 may not be quite as heavy as the old headline number suggested, or it may be heavier than the standard picture can explain, or both may be true at the same time in ways that expose how much of its size is really a measurement problem. Before we go further, if you like slow, careful science stories that respect your intelligence and take you somewhere strange by the end, subscribe. It helps this script find the people who want it, and it helps me keep making them. Now back to TON 6 Rain. The plan for tonight is simple. We are going to measure this thing, not with words, with images, with comparisons you can actually feel in your body. We are going to start with the dot in the photograph and end with the wall the number runs into. Along the way we will pass a light older than the Earth, a mouth wider than the solar system, and a growth story that current physics does not know how to tell. The strange part is not that TON 16 is huge. The strange part is what its size means. Because a black hole this large, at the distance TON 16 sits from us, should not be possible. Not in the time the universe had available, not with the fuel the early cosmos could deliver, not without breaking a limit that physics is supposed to enforce on every feeding black hole in existence. And yet, it is there, blazing at us across 10 billion years of empty space, older than the Sun, older than the Milky Way's spiral arms, older than almost every atom in your body, except the hydrogen, a light that left when the universe was less than a third of its current age, and only reached our telescopes recently enough that the first humans to look at it did not know what they were seeing. They thought it was a star. It was not a star. We're going to walk through what it actually is, how we know, what the newest measurements say, and why the answer to how big is TON 618 keeps changing depending on which paper you read and which method you trust. Get comfortable. Turn the lights down if you like. This is going to be one of those slow ones. We begin. In 1957, an astronomer at the Tenantzintla Observatory in Mexico was looking through photographic plates of the northern sky. The plates were part of a wide survey meant to catalogue objects that glowed unusually bright in ultraviolet light. Most of what showed up was already known. Blue stars. Hot young suns. Nothing surprising. But one dot did not fit. It sat in the constellation Canes Venatici, the hunting dogs, not far from the handle of the Big Dipper. It looked like a faint blue star. It was assigned an entry in the catalogue and given a number. TON 618. The TON came from Tenantzintla, and 618 was just the order in which it was logged. There was no reason to think it was anything special. For 13 years it sat in the catalogue untouched. Then, in 1970, a different survey went back and looked more closely. This time, astronomers measured the light from TON 618 across the whole spectrum, not just the ultraviolet band. And the light was strange. It was too red for a hot star. It had wide emission lines, the kind produced by gas moving at enormous speeds. The pattern matched something astronomers had only recently begun to understand. TON 6 maintain was a quasar. That word quasar sounds ordinary now. In 1970 it was almost a scandal. Quasars had only been identified a few years earlier, and nobody was fully sure what they were. They looked like faint blue dots, but they were not stars. They shone with the light of entire galaxies compressed into a single point. And they were far. Impossibly far. When astronomers measured how much the light from TON 618 was stretched by the expansion of the universe, they got a number that told them how long that light had been travelling. The light had been on its way for over 10 billion years. 10 billion years. Older than the Sun. Older than the solar system. Older than most of the stars visible to your eyes on a clear night. The dot on the photographic plate was not showing anyone what TON 618 looked like now. It was showing what it looked like when the universe was young, when the Earth had not yet formed, when the atoms that would eventually become the ocean and the atmosphere were still scattered gas somewhere in a slowly collapsing cloud. That should have been the end of the surprise. A very distant quasar, glowing across enormous time. Interesting, but not unique. The surprise came from the light itself. For a quasar to look as bright as TON 618 looked from Earth, given how far away it was, it had to be pouring out an amount of energy that made almost every other object in the sky look faint. Its light was not the light of a star. It was not even the light of a normal galaxy. It was, in raw output, brighter than 100 trillion suns combined, packed into a point smaller than a light year across. That kind of power does not come from stars. Stars burn fuel. Stars produce light by fusing hydrogen. There is a ceiling on how bright a single star can get, and even the brightest stars in the local universe fall billions of times short of what TON 618 was pouring into the sky. Whatever was making the light was not a star. Whatever was making the light was not a cluster of stars. Whatever was making the light was not even an ordinary galaxy. It was a single engine, and the engine had to be enormous. Astronomers already suspected by the 1970s that quasars were powered by supermassive black holes at the centres of very distant galaxies. Gas fell into the black hole, spiralled in, heated up, and radiated the energy of a small galaxy from a region no larger than the solar system. That model was still new, and it was still being fought over, but it was starting to hold. The question TON 618 forced was not whether it had a black hole at its centre. The question was how big that black hole had to be to explain the light. Because the brighter the quasar, the heavier the black hole needed to keep the light on. And TON 618 was pouring out so much light that the mass on the other side of the equation started to look absurd. That is where the real story of tonight begins. Not with the dot, with the number the dot pointed to. And that number is where the trouble starts. To measure a black hole you cannot see, you have to measure the things it is doing to everything around it. You cannot see the hole itself. You cannot even see the disk of gas around it in most cases. What you can see is the light of that gas, and the way the light is being stretched and shifted by the enormous speeds at which the gas is moving. Here is the trick. When gas falls toward a black hole, it does not fall straight in, it spirals. The closer to the black hole it gets, the faster it moves. Gas near the centre of the spiral moves at a large fraction of the speed of light. Gas farther out moves slower. All of this gas is glowing. because the friction of the spiral is heating it up enough to shine. If you look at the light from the whole spiral at once, you see a single spectrum. But that spectrum is smeared. Some of the gas is moving toward you, so its light is squeezed to shorter wavelengths toward the blue. Some of the gas is moving away from you, so its light is stretched to longer wavelengths toward the red. The result is that any single emission line, any single colour the gas would normally give off, gets spread into a wide, bulging band. The wider the band, the faster the gas is moving. And how fast the gas is moving tells you how much mass is pulling on it. That is the method. It has a name. Reverberation mapping and single epoch line width mapping are the two most common versions. Both work roughly the same way. Both use the width of a specific emission line, usually a line from hydrogen called H, to estimate how quickly the gas near the black hole is orbiting. Then, they use the brightness of the quasar to estimate how far out that gas is. From speed and distance, you can solve for mass. In 2004, a team led by Ohad Shemer at Tel Aviv University used exactly this method on TON 619. They looked at the width of the H line, they ran the numbers. The answer came back at about 66 billion times the mass of the Sun. That number is worth pausing on, not because it is a big number, but because of what it does to your sense of scale. The black hole at the centre of our own galaxy, the one every large telescope has been staring at for 30 years, weighs about 4 million solar masses. That is already a monster. The largest black holes commonly discussed at the centres of ordinary galaxies weigh around 1 billion solar masses. That is already extreme. TON 619, according to that 2004 measurement, weighed 66 times more than the biggest routinely quoted supermassive black holes, and about 16,000 times more than the one anchoring our own galaxy. It sat at the top of the mass ladder, above supermassive, in a category that some astronomers had begun to call ultramassive, meaning any black hole above 10 billion solar masses. At 66 billion, TON 619 was not just in that category. It was near the ceiling of it. For years, TON 618 was widely cited as one of the most massive black holes ever measured, and in many popular sources as the largest known. Blog posts and popular science videos ran the number without qualification. It became the standard answer to the question of how heavy a single black hole could get. If you have ever seen a diagram showing the size scale of black holes with a tiny dot for stellar mass, a small circle for supermassive, and a huge sphere for TON 619, that image was built on the 66 billion figure. Here is where you should feel the first crack in the story. That number was never certain. It carried an uncertainty of at least a factor of 2, sometimes more, depending on which assumptions you plugged into the equation. The H method depends on knowing exactly how the gas is distributed around the black hole. It depends on assuming the gas is moving in orbits and not being pushed by winds or radiation. It depends on calibrating your telescope carefully across a wavelength range that gets stretched a long way by the expansion of the universe when you are looking at something 10 billion light years away. Every one of those assumptions has been questioned since 2004. And in more recent years, the number has been tested again with different methods. What emerged is one of the strangest turns in the story of TON 6 Walt, because the same object can be pushed lower and higher depending on which method you trust. But before we get to that, we need to understand what a black hole that heavy would actually look like. Because when you translate 66 billion solar masses into a size, you get something that does not fit any picture you have in your head. You get a mouth larger than the solar system. There is a specific number that describes how big a non-spinning black hole is. It is called the Schwarzschild radius, named for the German physicist who worked it out in 1916 while serving on the Eastern Front in the First World War. The math is simple. The radius in meters is roughly 3 kilometers times the mass in solar masses, divided by 1. For our Sun, if you compressed it into a black hole, the Schwarzschild radius would be about 3 kilometers, about the width of a small city. For the black hole at the center of our galaxy, the Schwarzschild radius is about 12 million kilometers. That sounds enormous until you compare it to anything astronomical. It is about a fifth of the distance from Mercury to the Sun, a small ball at the scale of the inner solar system. For a billion solar mass black hole, the kind found at the centers of large modern galaxies, the Schwarzschild radius is about 3 billion kilometers. That reaches out roughly to the orbit of Uranus. Now do the math for TON 618 at 66 billion solar masses. The Schwarzschild radius comes out to about 200 billion kilometers. 200 billion kilometers is not a distance you can picture. It is a number you have to translate. So here is the translation. Neptune, the outermost planet in our solar system, sits about 4.5 billion kilometers from the Sun. At the 66 billion solar mass estimate, TON 618's Schwarzschild radius would be roughly 200 billion kilometers, about 40 to 45 times Neptune's distance from the Sun. Its full event horizon diameter would be roughly twice that. The entire orbit of Neptune, in either direction from the Sun, would sit deep inside the black hole with room to spare. Even that is hard to feel. So try a different scale. Light, which crosses the Earth to Moon distance in a little over a second, and which crosses from the Sun to the Earth in about 8 minutes, would need somewhere close to a week and a half to travel from one side of TON 618's event horizon to the other. The mouth of this hole is not measured in miles or kilometers, it is measured in days of travel at the speed of light. If you built a spacecraft that could travel at the speed of Voyager 1, currently the fastest human-made object leaving the solar system, and you launched it across the event horizon of TON 618, it would take that spacecraft roughly 400,000 years to cross from one edge to the other. That is not a trip across a solar system, that is a trip across a good fraction of the distance between neighbouring stars. The event horizon is not the black hole itself, it is only the boundary. It is the surface at which the escape speed equals the speed of light, the point past which nothing that falls in can come back. The actual singularity, the point of infinite density predicted by the mathematics, sits at the very centre. The event horizon is just the door. But the door of TON 618, at the 2004 mass estimate, is wider than the space our species has ever travelled. The Voyager probes, the deepest man-made objects in space, have been travelling for nearly 50 years and have barely crossed the boundary of the Sun's magnetic bubble. The full distance they have covered is a rounding error compared to the diameter of TON 618's event horizon. You are being asked to accept physically that a single object in the universe has a boundary large enough to swallow every star system within a small stellar neighbourhood all in one gulp and still have room for more. And here is the part that is easy to miss. An event horizon this big does not mean the black hole itself is a large physical object. Black holes do not have a surface. The mass is not distributed inside the horizon like a planet. The horizon is a purely geometric boundary. It is the size of the region from which light cannot escape, not the size of anything solid. But that geometric boundary matters because it sets the scale of everything happening around the black hole. The disk of gas feeding TON 618 has to be even wider than the horizon. The dust and gas swirling within the black hole's influence extends light years beyond the horizon, and the light we see, the quasar itself, is coming from the region just outside the horizon, where infalling matter reaches its highest temperatures. If you could stand somewhere far enough back to see Ton 618 Hole, you would not see a solar system-sized dot. You would see a glowing region larger than most nearby galactic nuclei, wrapped around a shadow the size of the local stellar neighbourhood. There is a useful thought experiment for feeling this. If Ton 618 replaced Sagittarius A star at the centre of the Milky Way, its event horizon would dwarf the solar system, but it would still be tiny compared with the full scale of the galaxy. Stars thousands of light years away would not suddenly be inside the horizon. They would orbit a much more massive central object, and the inner galaxy would be radically reshaped over time. The stellar orbits close to the galactic centre would tighten and warp. Gas and dust for many light years around the core would be pulled into a feeding disk far larger than the one Sagittarius A star quietly maintains today. The night sky, seen from Earth, would be dominated not by the black hole itself, which is still far too small in angular size to see directly, but by the light of everything falling toward it. That is what the number 66 billion actually looks like in place. Not a horizon that swallows the local stellar neighbourhood, but a gravitational engine strong enough to reorganize the inner galaxy around itself. That shadow is what we are trying to measure. That shadow is the thing whose exact mass keeps refusing to settle. Before we talk about how the mass estimate has changed, we need to talk about the light. Because the reason Ton 618 shows up in the first place, the reason anybody in Mexico saw a bright dot on a photographic plate in 1957, is that this black hole is one of the brightest single objects in the observable universe. Not by a small margin, by a huge one. The Sun produces about 4 times 10 to the 26th watts of power. That is a bright star. The Milky Way galaxy, all 100 billion or so of its stars combined, produces roughly 100 billion times more. That is the light of a galaxy. Ton 618 pours out roughly 4 times 10 to the 40th watts. That is on the order of 100 trillion times the luminosity of the Sun, and roughly 1,000 times the light of a large galaxy like the Milky Way. A single point in the sky, brighter than the combined output of 1,000 ordinary galaxies, sustained continuously for the length of time it has been observed. Where is that energy coming from? Not the black hole itself. Black holes do not emit light. What emits the light is the accretion disk, the swirling ring of gas and dust that is falling toward the horizon but has not yet crossed it. As that material spirals inward, it heats up through friction. The closer it gets to the black hole, the hotter it becomes. Near the innermost edge of the disk, temperatures reach tens of thousands of degrees, sometimes more. Hot matter shines. For most stars, the light produced comes from nuclear fusion, hydrogen turning into helium in the core. The efficiency of that process is famously low. About 0.7% of the mass of the hydrogen ends up as light. The rest stays as matter. The disk around a black hole is different. When gas falls to the innermost stable orbit and then over the edge of the event horizon, its potential energy is converted into light with an efficiency that can reach 10 to 40% depending on how fast the black hole is spinning. That is roughly 50 times more efficient than the fusion that powers the Sun. That efficiency is what lets a single black hole outshine an entire galaxy of stars. Feed enough matter into the disk at the maximum rate the physics allows, and the light output becomes staggering. For Ton 618, the light output implies a feeding rate of hundreds of solar masses of gas being swallowed every year. That is not a stable long-term rate. That is the rate of an object gorging itself on whatever material happens to be within reach of its gravity. Now, look at the sky. Every point of light you can see with your naked eye on a clear night is a star inside our own galaxy. Every fuzzy patch you can see with a small telescope, if it is not another star cluster, is another galaxy. The most distant thing you can see with the naked eye is the Andromeda galaxy, about 2.5 million light-years away, and you can see it because it contains 1 trillion stars glowing together. If TON 618 were placed at the distance of Andromeda, it would dominate the night sky as an intensely bright point-like source, outshining any ordinary galaxy. Where Andromeda today appears as a faint smudge, only barely visible to the naked eye, TON 618 at that distance would appear as a sharp, brilliant point, easily the most striking object in the sky after the Sun and Moon. But TON 618 is not at Andromeda's distance, it is 4,000 times farther. And it is still bright enough to catch light on a photographic plate from a small observatory in Mexico. That is what we mean when we say it is one of the most luminous objects known. The strange part is that this luminosity is a physical limit. There is a ceiling on how brightly a feeding black hole can shine. It is called the Eddington limit, and it comes from a simple physical principle. As light streams out of the accretion disk, it exerts pressure on the gas still falling in. If the light is too bright, the pressure of the outgoing radiation pushes the incoming gas away faster than gravity can pull it in. The feeding shuts itself off. The Eddington limit is not a soft guideline. It is a physical wall. Push against it too hard, and the black hole loses its own fuel supply. Every measurement of TON 618's brightness sits at, or in some estimates above, its Eddington limit. That is a strange fact. It means this black hole is feeding at the maximum rate that physics allows, right at the boundary where the process should stall itself. That gives us a clue about the number we started with. If TON 618 were less massive than 66 billion solar masses, it should not be able to shine this brightly, because the Eddington limit for a smaller black hole is lower. If it were more massive, then it would not be at the limit at all, and we would expect it to look less extreme. Sitting exactly at the Eddington limit is one of the clues astronomers have used to check the mass estimate, and that check in more recent work has begun to shift. The shift changes what we thought TON 618 was. Before we can trust any mass estimate, we have to trust the distance. Because a wrong distance to a quasar throws off almost every other number you calculate about it. The brightness we measure is only the brightness that reaches us. The true brightness, the raw output, depends on how much space that light had to spread out across before it got here. The distance to TON 618 is calculated from the redshift of its light. Here is what that means. When light travels through an expanding universe, its wavelength gets stretched. Blue light becomes greener. Green light becomes redder. Red light becomes infrared. The amount of stretch tells you how much the universe has expanded during the time the light was in flight. For TON 618, the redshift is about 2.219. That number is a factor. It tells you that the wavelength of every emission line from TON 618 has been stretched to more than 3 times its original value by the time it reaches Earth. Translate that into distance, and you get a number that depends on what you mean by distance. There is the light travel distance, which is the time the light has been on its way. For TON 618, that is about 10.4 billion years. There is the moving distance, which accounts for how much the universe has expanded since the light left, and which for TON 617 is closer to 17 or 18 billion light-years. And there is the distance at the moment the light was emitted, which is much smaller than either of those. Most popular articles quote the 10.4 billion light-year figure, because it matches the time humans understand best. When you say the light has been travelling for 10.4 billion years, you are saying that TON 618, as we see it, existed 10.4 billion years ago. That is a long time. The Sun and the Solar System formed only about 4.6 billion years ago. The Earth is younger than the light in this photograph. The light that hit that Mexican photographic plate in 1957 had been on its way since long before the Sun had begun to fuse hydrogen. Since long before the atoms that make up your bones were forged in dying stars. Since a time when the universe was less than a third of its current age. When the first generation of galaxies was still assembling itself out of raw hydrogen and helium. TON 618 was already there, feeding, blazing alone at the centre of a galaxy that was probably still under construction around it. The strangeness of this fact matters, because it puts a hard clock on how the black hole grew. The universe, at the moment we are seeing TON 618, was about 3 billion years old. The Big Bang had happened, the first stars had formed, the first galaxies had begun to assemble. Some of the very first stellar mass black holes had probably already been created by the death of massive early stars. But the amount of time available for any of them to grow to enormous size was limited. 3 billion years is not a lot when you are trying to grow a black hole. At the Eddington limit, the fastest sustainable feeding rate we know of, a black hole roughly doubles its mass every 30 to 50 million years. Start from a stellar mass black hole of 30 solar masses. Feed at the maximum rate the whole time, without interruption, for 3 billion years. You get somewhere between 100 million and a few billion solar masses depending on your assumptions. You do not get 66 billion. You do not even come close. To reach 66 billion solar masses in less than 3 billion years, TON 618 would have had to grow faster than the Eddington limit for extended periods, or start from a seed that was already massive, or benefit from mergers with other giant black holes, or some combination of all three. This is not a new problem. It is the same problem that has been forcing astronomers to consider strange formation channels for supermassive black holes for 2 decades. Direct collapse, super Eddington feeding, seed mergers in dense environments. All of these are possible. None of them is fully established. TON 618 sits inside that puzzle at the extreme end. It is one of the objects that makes the puzzle real. If the mass is correct, then something extraordinary happened at the centre of that early galaxy. Either an enormous gas cloud collapsed directly into a heavy seed black hole, skipping the star phase entirely, and then fed at the maximum rate for nearly the whole age of the early universe. Or many smaller black holes merged in a way we have not yet observed anywhere else. If the mass is wrong, then a lot of things become easier. Which is why, in more recent years, astronomers have gone back to the data and asked whether the number was as solid as everyone had been treating it. The 2004 mass estimate of about 66 billion solar masses was based on a single measurement method applied to a single spectrum using assumptions that were the best available at the time. It was published, cited, and passed into the mainstream. TON 618 became, in popular astronomy, one of the most massive black holes ever measured. The problem is that the same object has since been revisited with different emission line methods and improved calibrations. And when the newer measurements are compared, the numbers do not all agree. In recent years, astronomers have revisited that old 66 billion solar mass figure. Some newer estimates place TON 618 close to about 40 billion solar masses, while the older 66 billion figure remains widely cited. The result is not a clean correction, it is a measurement uncertainty problem. The specific correction is subtle. The 2004 measurement used a scaling relationship called the R to L relation that connects the size of the broad line region around a quasar to the quasar's luminosity. That relation was calibrated from a set of nearby, less extreme quasars. When applied to TON 618, an object far more luminous than anything in the calibration set, the relation has to be extrapolated well past the range where it has been tested. Later analyses have argued that this extrapolation systematically inflates the inferred distance from the black hole to the gas producing the H-line, which in turn inflates the mass estimate. Shrink the assumed distance from the black hole to the gas by a factor of about 1.6, keeping everything else the same, and the mass estimate drops by roughly the same factor. That is where the shift from about 66 billion to around 40 billion comes from. It is not a discovery of new data. It is a rethinking of how confidently the old scaling relation can be applied at the extremes. Meanwhile, other analyses that account for radiation-driven winds in the gas around the black hole have argued that the standard method may actually underestimate the mass, because winds broaden the emission line beyond what pure orbital motion would produce. Correct for that broadening, and the mass can come out even higher. In this picture, the width of the H-line is a mixture of two things: gas orbiting the black hole, and gas being blown outward by the intense radiation pressure of the disk. The orbital component tells you about mass. The outflow component tells you nothing about mass, but it makes the line look wider than it should. Fail to separate the two, and you overestimate the orbital speed, which means you overestimate the mass. The direction of the correction in that analysis depends on how much of the line width you attribute to outflows. Assume most of it is outflow, and the mass shrinks. Assume very little is outflow, and the mass grows past what the standard method would give you. There is no clean way to decide from a single spectrum alone. You need repeated observations, taken across months or years, to watch how the line responds to changes in the quasar's brightness. Only a handful of quasars have been studied that way, and TON 618 is not yet one of them at high resolution. Neither result is conclusive. Both are, as of the time of this recording, part of ongoing analysis. What we can say honestly is this: TON 618 is almost certainly ultramassive, likely in the tens of billions of solar masses. The commonly cited values cluster around roughly 40 to 66 billion solar masses, depending on method and assumptions. The exact number and TON 618's place among the heaviest known candidates is not settled. That might feel like a letdown. You came into this script expecting a clean answer, and instead you are being told that the number floats. But here is why it matters that the number floats. Because the way we measure the mass of a distant black hole tells us how well we understand the physics of gas around black holes in general. If different methods give different answers, that means one or more of the methods is missing something. It might be the winds, it might be the disk geometry, it might be that the accretion in ultramassive black holes behaves differently from the accretion in ordinary supermassive black holes. Any one of those possibilities changes how we interpret quasars across the whole universe. There is another wrinkle. As telescopes have gotten better, other candidates for the title of heaviest known black hole have entered the picture. Phoenix A, at the center of the Phoenix cluster of galaxies, has been estimated at up to 100 billion solar masses by some methods, based on how it warps the light and dynamics of stars around it. That estimate is also uncertain, and probably overstated in many popular sources, but it exists in the same range as TON 618. The black hole in the center of the giant elliptical galaxy IC 1101 has been estimated at tens of billions of solar masses, though not as high as TON 618. The black hole in the center of NGC 4889 has been measured by different methods at somewhere between 6 and 37 billion solar masses. None of these has a clean, undisputed measurement. All of them sit in the ultramassive range. TON 618 was, for a long time, considered the champion by default because its number was the largest published. Whether it still holds that title depends on which paper you cite. What we can say with confidence is that TON 618 is in the top handful of the heaviest single black holes ever measured, that it is by far the brightest quasar known at high mass, and that its existence forces the same difficult question that all ultramassive black holes force. How did the universe make something this large this early? That is the question we can circle around, and even attack, but not yet answer. The answer requires new observations of a kind that only the newest generation of telescopes is capable of collecting, which is why TON 618 is not a closed case in astronomy, it is an open one, and it may stay open for another generation. To feel why the size of TON 618 is a problem for physics, you have to understand the feeding limit properly. It is one of those principles that sounds like it should have exceptions, but almost never does. When gas falls toward a black hole, the gas heats up. When gas is hot, it glows. When it glows, it produces light. And light, contrary to how it feels when you stand in the sun, has physical pressure. Photons carry momentum. When they push against something, they exert a force. For a feeding black hole, the light is pushing outward. The gravity of the black hole is pulling inward. If the light is faint, gravity wins, and gas falls in easily. If the light is bright, the outward push from photons starts to shove gas away before it can be swallowed. The exact brightness at which the two forces balance is called the Eddington limit. Above the limit, feeding slows down or stops. Below the limit, feeding continues. For a small black hole, the Eddington limit is low, so the gas has to feed slowly. For a large black hole, the Eddington limit is high, so the gas can feed quickly. But even for a very massive black hole, the limit sets a maximum growth rate. That maximum growth rate translates into a doubling time. At the Eddington limit, a black hole doubles its mass roughly every 30 to 50 million years, depending on how much of the infalling mass ends up as light and how much crosses the event horizon as matter. Now start a clock at the moment the first massive stars died and left behind stellar mass black holes, roughly 100 million years after the Big Bang. From that moment, run the doubling clock forward at the Eddington limit, without interruption, for the entire remaining time until we observe TON 618 as it existed at 10.4 billion light-years distance. That is about 3 billion years of Eddington limited growth. That is enough to double a mass roughly 60 to 100 times. Starting from 30 solar masses and doubling 60 times gets you to about 30 billion. Starting from 30 solar masses and doubling 100 times gets you to about 30 trillion. So on paper, if the doubling never pauses, if the fuel supply never runs out, if the black hole feeds at the exact limit for the entire cosmic clock, you can reach TON 618's mass. But the doubling never runs uninterrupted in real life. Feeding stops. Fuel runs out, environments change, neighbouring galaxies interfere. The realistic growth rate for a black hole feeding across cosmic time is much lower than the theoretical Eddington maximum. For TON 618 to exist, it has to have fed either much faster than Eddington for some period, or much more consistently than we would expect any real gas supply to allow. Or it has to have started as something larger than a stellar mass black hole in the first place. That is where the direct collapse idea comes in. In the very early universe, before stars had polluted the gas with heavier elements, some gas clouds may have been so cold, so dense, and so undisturbed by radiation that they collapsed directly into black holes of 10,000 to 100,000 solar masses without ever forming stars. These are called heavy seeds. From a heavy seed, the doubling clock has fewer doublings to run, and the mass at the end of the same 3 billion years can be much higher. TON 618 in this picture could have started as a 100,000 solar mass heavy seed, or larger. From there, standard Eddington feeding for 3 billion years is enough to reach tens of billions of solar masses without any special tricks. The problem is that we have never directly observed a heavy seed forming. The physics is possible, the observational evidence is thin. Recent JBUS observations have found candidate objects that behave like they might be heavy seeds observed early, but none of the identifications is conclusive. The alternative is super Eddington feeding, at least for some fraction of the growth. That means feeding at rates that exceed the theoretical maximum. In some models, super Eddington feeding is possible for short periods, when gas is being funneled in through a channel that shields the outgoing radiation from the incoming gas. The disk becomes optically thick along the feeding direction, and the gas can pour in almost freely. This has been observed, in weaker form, in a few local ultra-luminous X-ray sources. Whether it can happen in the early universe on the scale needed to grow a TON 618 in 3 billion years is one of the questions the current generation of telescopes is designed to test. So when someone asks how big TON 618 is exactly, the honest answer is not just a number. It is a set of possible numbers, each of which implies a slightly different story about how the early universe made its most extreme objects. A 40 billion solar mass TON 618 is challenging but reachable with heavy seeds and steady feeding. A 66 billion solar mass TON 618 pushes the timeline harder. Anything meaningfully above that would require growth channels we do not currently understand. The question is not just how heavy, the question is what its heaviness implies about the physics we thought we knew. TON 618 does not sit in empty space, it sits at the centre of a galaxy. That galaxy has never been imaged directly, because the light of the quasar itself outshines everything around it. From Earth, we see the quasar. The host galaxy is buried in its glare, but there are ways to estimate what that galaxy must be like. In the modern universe, black holes and their host galaxies follow a strict relationship. The more massive the black hole, the more massive the galaxy. The ratio is not exact, but it is tight. A galaxy with a stellar mass of about 1 trillion suns, at the upper end of what large modern galaxies produce, tends to host a central black hole of about 1 billion solar masses. If TON 618 followed that ratio at 40 to 66 billion solar masses, its host galaxy would have to contain roughly 40 to 66 trillion solar masses of stars. That is a galaxy roughly 40 to 100 times the mass of the Milky Way. A galaxy near the upper limit of any galaxy known to exist. The problem is that at the redshift of TON 618, the universe had only had 3 billion years to build any galaxy at all. Producing a 40 trillion solar mass stellar host in that time is even harder than producing the black hole itself. So one of two things must be true. Either TON 619 lives in a genuinely enormous host galaxy that grew impossibly fast, and the mass ratio between black holes and their hosts was already established at the earliest cosmic epochs. Or TON 619 lives in a smaller galaxy than the ratio predicts, meaning it is what astronomers now call an overmassive black hole ahead of its host in growth. The evidence from other high redshift quasars observed with JWST points toward the second option. The little red dot studies have shown that many early black holes were disproportionately large for their host galaxies. The ratio between black hole and galaxy that we see in the modern universe was not fixed at the beginning. It developed later. Early on, black holes may have grown faster than their surrounding galaxies could keep up with. TON 619 fits inside this picture. It is likely a black hole that formed and grew ahead of its host, dominating the mass of the early galaxy in a way that no modern galaxy would tolerate. The galaxy caught up later, if the galaxy survived at all. This changes the mental image you should have of TON 16 in its youth. It was not a peaceful giant sitting at the middle of a well-organized galaxy. It was a runaway engine at the center of a smaller structure, growing faster than everything around it, blowing enormous winds of hot gas out into the space beyond it, sculpting the environment around it through its own radiation. The quasar phase is not gentle. When a black hole is feeding at the Eddington limit, it produces winds and jets that carry away roughly as much energy as the star formation of an entire galaxy. Those winds heat the surrounding gas, shove it outward, and can slow down the assembly of the host galaxy itself. This process is called quasar feedback. It is thought to be one of the mechanisms that eventually stops galaxies from growing any bigger. TON 619 in its youth was probably feeding, blowing, and shaping its host galaxy all at once. The environment we see, if we could see it, would be a mess of hot gas, disturbed star formation, and outflowing material stretching for tens of thousands of light years around the quasar itself. Around all of that would be a dark matter halo, which is the invisible scaffolding every galaxy sits inside. Dark matter does not emit light, it only makes itself known through gravity. But every large galaxy in the modern universe is embedded in a halo of dark matter that outweighs the visible stars by a factor of 5 to 10. For a galaxy massive enough to host TON 618, the surrounding dark matter halo would likely weigh well over 1 trillion solar masses, possibly 10 trillion or more. It would be one of the rarest, densest concentrations of dark matter that existed anywhere in the universe at that early epoch. Such halos are not evenly distributed. They form at the crossing points of the cosmic web, where filaments of dark matter and gas meet. The most massive early halos, the ones that could feed a black hole like TON 618, would sit at the busiest cosmic intersections, drawing gas in along multiple streams at once. That constant infall may be part of the reason feeding at the Eddington limit could be sustained for as long as it was. Fuel kept arriving because the entire large-scale environment was funneling it toward the center. If that picture is right, then TON 618 is not just a strange object. It is a probe of where in the cosmic web the most extreme conditions existed. Find more TON 618 class quasars at similar redshifts, map their positions, and you get a map of the most powerful early nodes of large-scale structure. The largest black holes are, in this sense, cosmic addresses. They mark the places where everything went right or wrong at the same time. That environment over the last 10.4 billion years has evolved. TON 618 as we see it is not TON 618 as it is now. Whatever happened next, we are not seeing. The light from later stages of its life has not reached us yet, because the universe has expanded so much in the meantime that TON 618's present state is now unreachable to us in any observational way. Whatever it is doing today, the record of that time will not reach any Earth telescope for another set of billions of years, and by then, none of the observatories that exist today will still be running. We are watching a fossil light show. The performers moved on long ago. What we call TON 618 is the light of a burning that already ended, or that transformed into something so calm that no light from the calm phase would ever have reached this far. Which raises a question that closes the loop for tonight. What happens to a black hole this large when its feeding phase ends? Where does an ultramassive black hole go after it stops being a quasar? TON 618 as we observe it is not a stable long-term state. A quasar cannot feed at the Eddington limit forever. The gas supply that fuels it is finite. As the surrounding galaxy consumes or expels its available gas, the feeding slows. The disk fades. The bright dot on a photographic plate becomes something else. At some point, likely within a few 100 million years of the epoch we are watching, TON 618 would have run out of dense fuel. Its disk would have thinned. Its light output would have collapsed by a factor of 1,000 or more. It would have become, for practical purposes, invisible. The black hole itself, of course, does not go anywhere. It stays exactly where it is. What changes is its behavior. In the modern universe, we can see what dormant supermassive black holes look like. Sagittarius A star, at the center of our own galaxy, is one. It weighs about 4 million solar masses. It is barely feeding. Its total light output is roughly 100 million times fainter than the smallest active quasar. Compared to what it must have been during its own active phase, in the distant past, it is quiet. Something like that is likely happening to TON 618 now, on the other side of the 10.4 billion year light delay. It is probably a quiet, ultramassive dark center in an old galaxy, feeding slowly on whatever gas drifts near, occasionally flaring when a star gets too close, mostly still. But that quiet giant would still be one of the largest single objects in the known universe. Its event horizon would still be measured in light days across. Its influence would still shape the motions of stars for light years around it. We will probably never see it in that state. The light from a dormant TON 618 would be so faint that no current or planned telescope could detect it across 10 billion years of expanding space. All we get is the light from its youth. There is a strange kind of loneliness in that fact. Every measurement of TON 618 that anyone has ever made or ever will make from Earth comes from a single blazing moment in its history. A moment when it was feeding hard, growing fast, and pouring out enough light to reach across the entire observable universe. That moment is what defines it in our catalogues. That moment is what appears in every diagram. That moment is what its name refers to. But that moment ended, long before humans looked up, long before humans existed to look up. TON 618 as a quasar is a story that already concluded in the reference frame of the object itself. What we see is the delayed announcement of that ending, travelling toward us across the expanding fabric of space. By the time you finish watching this script, some tiny additional fraction of TON 618's youth will have arrived at Earth. The light will have crept a little further. 10 more minutes of that ancient feeding will have entered a telescope somewhere. Then the light will keep going past Earth, past the Sun, out into deep space, without ever stopping. The photons from TON 618's brightest phase will spread outward through the universe for the rest of cosmic time. Some of them will be intercepted by distant future observers. Most of them will just travel, unobserved, until they redshift into wavelengths so long that they blend indistinguishably with the background of the universe. The record of TON 618's most extreme moment is being spread across cosmic time like ink diffusing through water. In 100 billion years, when the universe has expanded far enough that no galaxy is visible from any other, the last observer capable of detecting TON 618's light will be somewhere very close to Earth, watching the same faint red glow we watch, and asking the same questions we are asking tonight. The number will still float, the mystery of how it grew will still be open. The answer to how big TON 618 is exactly will still, in some final sense, depend on how you measure it. Here is where we stand. TON 618 is a black hole. It is almost certainly ultramassive, likely in the tens of billions of solar masses. The commonly cited values cluster around roughly 40 to 66 billion, depending on method and assumptions. The older 66 billion figure remains widely known. Some newer analyses place the number closer to 40 billion. Neither value has been directly measured from resolved gas motion. Both are inferred from the width of a single emission line, run through models whose calibrations have to be extrapolated well past the range where they were tested. The Schwarzschild radius, at the 66 billion figure, is about 200 billion kilometers, roughly 40 to 45 times Neptune's distance from the Sun. Its diameter is about twice that. Even at the lower 40 billion estimate, the horizon is still wider than the entire solar system by a very large margin. The distance to TON 618 is about 10.4 billion light-years by light travel time, meaning we see it as it existed roughly 3 billion years after the Big Bang, at a moment when the universe was less than a quarter of its current age. Its brightness is roughly 100 trillion times that of the Sun, or 1,000 times that of the entire Milky Way. It sits at or near the Eddington limit for its mass, meaning it is feeding as fast as any black hole is thought to be able to feed and still shine in the ordinary way. Its host galaxy is invisible in the glare of the quasar and can only be inferred. Depending on the ratio you assume, the host would either have to be enormous, or TON 618 would have to be an overmassive black hole ahead of its galaxy in growth. The current best guesses lean toward the second option. The formation story is not fully known. Standard stellar mass seed models, feeding at the Eddington limit for the entire available time, struggle to produce a black hole this large this early. Heavy seed models, in which black holes form from the direct collapse of primordial gas clouds, work more easily, but have not been directly observed. Super Eddington feeding may fill part of the gap. The complete picture is under active investigation. All of that is what we know. Here is what is easy to miss. Every number in the paragraph you just read is the result of light that had to travel across an expanding universe for longer than the Sun has existed. Every number is an inference from that light, run through models and calibrations and assumptions. Every number has an error bar. Every number has been revised at least once. Every number will probably be revised again. The size of TON 618 is not a fixed fact. It is a running estimate. It floats within a range, and inside that range are stories about how the early universe worked. If TON 618 is closer to 40 billion solar masses, one story is more plausible. If it sits near the older 66 billion figure, a harder story becomes necessary. The number itself is a probe. That is how astronomy works. It is not a series of settled facts pinned to a chart. It is a set of measurements that keep sharpening, keep shifting, and keep raising new questions. Ton 6618 has spent nearly 70 years teaching astronomers how difficult it is to measure a distant black hole. It will probably spend another 70 teaching us more. And the strangest thing about the whole story is that we can measure this monster at all. A dot on a photographic plate, barely visible, recognized as unusual only because of its color. Followed up decades later because someone thought to check whether it might be something more than a star. Weighed by tracing the width of a single hydrogen line in a spectrum stretched across 10 billion years of expansion. Assigned a number that no human sense can meaningfully process, and that hangs on assumptions no human has ever directly tested. That is the answer to the question we started with. Ton 618 is exactly this big. And the exactly is the part that keeps moving. The answer floats, but every one of the numbers it floats between is enormous enough to overwhelm any part of your intuition that was built for the world you can see. The largest thing in the sky you have ever noticed is the moon. Its width is about half a degree from your point of view. Ton 618's event horizon, at its measured distance, is far too small to see even with the largest telescope on Earth. But if you could somehow bring Ton 618 close enough to appear the size of the moon, its actual physical size at that distance would be so absurd that any nearby star system would be lost inside the horizon many times over. That is what tens of billions of solar masses in one place produces. That is what the number turns into when you put it into a place you can imagine, and somewhere in the sky, in the constellation of the hunting dogs, that is what is really there. Not a star. Not a galaxy. A single point on the sky where the universe made something that behaves like a wall in the mass equations of physics. A wall we are still trying to describe. A wall whose exact height we cannot yet agree on. The dot in the 1957 catalogue was labelled Ton 618 because of where it was catalogued and in what order. It could have been given a more dramatic name. It was not. It is a number and a letter code assigned by a small observatory in Mexico, attached forever to what may be the heaviest single object anyone has ever measured. The plate is old. The name is small. The thing is enormous. Tomorrow, the light from Ton 618 that is currently in flight will still be in flight. In 100 years, it will still be arriving at Earth. In 1,000,000 years, some of it will still be travelling past the outer parts of what our galaxy will have become by then. There is no version of the future in which this light stops. It just spreads, which means there is a real sense in which Ton 618 will keep being observed, in one form or another, for the rest of the age of the universe. Somewhere, at every future moment, a photon that left that black hole's accretion disk 10.4 billion years ago will still be finding its way into some instrument, or off some dust grain, or across some empty space. That is the last size of Ton 618, not its diameter, not its mass. The size of the light it left behind, spreading forever, carrying a record of the moment it was brightest, across a universe that has no way of forgetting. If this script gave you a way to feel that scale, subscribe. It genuinely helps the channel find the people who want to sit with these questions for as long as they take. There are more of them coming. For now, close your eyes if you can, picture the dot, Picture the 10 billion years of empty space between it and you. Picture the light still moving through the dark. Good night.